Let's start band structure calculation. For the band structure calculation, the important thing is that we must know the correct Brilliant zone path for the set structure, whether it is BCC, simple cubic, FCC, tetragonal, orthorhombic, or whatever it is. So let's move on to see what is that. So in the next slide, we will see. So here you can see that this is the basically the Brilliant zone path for this simple cubic structure with lattices is A00, A1, A2 is equal to 0, A0, and A3 is 0, 0, A. So this structure has a Brilliant zone path from gamma to X, X to M to gamma, and gamma to R, and R to X, and then M to R. So this is basically, and these are the symmetry structure. So when we use this part, then we will get the band structure. Here you can see that this is the band structure for this simple cubic structure, which is SR SNO3 in cubic lattice. So how to do this? How to put this band line or the Brilliant zone path in the input file. So here you can see this is a band line scale and black band lines. And number one point is that 0, 0, so gamma always lies on 0, 0. And from gamma to M, here you can see 18 points. From M to K, 16 points. And this from K to gamma is 9 points. From gamma to A is 13 points. And from A to L, it is 15 points. So how we can put these Brilliant zone path in the input file. So let me show you. So here it is the input file. So the first thing is after optimization, we will calculate single point calculation. What does single point mean? Single point means that here you can see that label and the system label name, which structure I am going to study. And here you can see optimization, MD type of run we commented, hash with hash, and MD number of CG steps is 9000. This is also commented with hash and variables. So either you can follow this way or you can even you can remove this step. You can you should not include like this way. Okay, so uh, this is one thing. The other thing is that so it will be single point calculation. Just one step it will go and it will give you the band lines. So the rest of the thing is the same. Mesh cutoff is 200 RY and which correlation function you are using. So GJ and PBE. So here I will show you. And before going to the article, first we will discuss the band lines. So here. So then these band lines we took from the Brilliant zone path. So here you can see for gamma we will take only 1 point, okay, and it is at 0, 0. And from gamma to M, here we consider 9 points. So these points depends on your requirement, how many points you want. If you want number of points, then you can increase these numbers. And from gamma to M9, from M to K8, and from K to gamma 4 points, and from gamma to A 6 points, and from A to L 7 points. So when we include this block in the input file and we run the calculation for single point, so it will give us the output file which we will require bands output file it will give us in the output, and that band file here you can see we will take after completion copy this file name band file to the SIESTA utility. In the utility there is a band folder, and you can copy here. If you are doing this for the first time, then first you need to run this make command, and after that you can dot slash gnu band and your material the output file from the single point calculation, and you will give the output name, and that output when you run it, it will give you an output file. That output file you can bring to the origin, and you can visualize the structure. If your band energy band gap is not correct, then you can apply the U block, and U value usually varies from 0 to 14. So you need to check that stepwise. Okay, and after that you will get the band line corrected band structure. Okay, so let me show you for this is for the sample cubic, and for the BCC. Here you can see this is the BCC structure, and here is the band line path. Okay, so you can calculate the this is for the uh, body center cubic structure, and you can get this type of results. And the same for the FCC, and the same for the tetragonal structure, and the many. Thank you so much.